Welcome to Part 2. Carbon resides in many reservoirs at or near the Earth's surface, ranging in size from the relative tiny amounts of carbon found in atmospheric methane to the tremendous amounts of carbon found in sedimentary rocks. One of our goals is to understand how this system of reservoirs responds to perturbations. We will use the response to the release of carbon dioxide from the burning of fossil fuels as an example of the dynamics of the carbon cycle and of the material recycling systems in general. This animation, produced by NASA, shows the global biosphere in the background and the corresponding carbon dioxide graph in the foreground. The biosphere is represented as phytoplankton concentrations over the ocean and vegetation index over land. The carbon dioxide concentrations are from measurements made in Mauna Loa in Hawaii. As each year progresses, notice how the greening of the land moves south to north, then north to south. Also notice how this corresponds to the carbon dioxide graph. The carbon dioxide content falls during the northern hemisphere summer, when photosynthesis surpasses respiration and decomposition. It then rises during the late autumn to early spring, when respiration and decomposition of the previous season's crop of leaves exceeds photosynthesis. These are annual oscillations in the carbon dioxide graph. However, the overall carbon dioxide trend from 1980 to 2005 is upward. The atmosphere is a reservoir of carbon in the form of carbon dioxide. Reservoirs are typically characterized in terms of the amount of material they are holding at any particular time. In this figure, the amount of carbon is expressed in gigatons of carbon. A gigaton is 1 billion metric tons, and 1 metric ton is 1,000 kilograms. With the notation GTC, we are keeping track of the mass of only the carbon atoms, not the other atoms to which they are attached. Reservoirs are temporary repositories for material that flows through them, and their size changes in response to imbalances between inflow and outflow. The inflow to the atmospheric carbon dioxide reservoir is a combination of the processes of respiration and decomposition. This inflow can be expressed in units of gigatons of carbon per year. The outflow from this reservoir is photosynthesis, and the rate of outflow is also expressed as gigatons of carbon per year. If the rates of inflow and outflow were such that the atmospheric carbon dioxide level remained at a constant value with time, we would say that steady state had been achieved. Steady state is a condition in which the state of the system component is constant with time. Steady state could be achieved if no inflow and no outflow existed, that is, if both processes ceased. A constant level could also be maintained if the rate of inflow of carbon dioxide into the atmosphere equaled the rate of outflow. Any imbalance in these rates leads to a change in the level of atmospheric carbon dioxide. When the inflow exceeds the outflow, the atmospheric carbon dioxide level rises. This situation is analogous to the Northern Hemisphere winter condition. When the outflow exceeds the inflow, the level falls, analogous to the Northern Hemisphere summer condition. Steady state can be maintained over time only if the rates of inflow and/or outflow are sensitive to changes in the size of the reservoir. This means that there must be couplings that link the reservoir size to the processes that govern inflow and outflow. Consider what would happen if a reservoir in steady state were perturbed by an addition of material. If the coupling governing inflow was negative, or if that governing outflow was positive, that is, inflow decreased or outflow increased, the reservoir would return to its original state. One such negative feedback loop exists between the photosynthetic rate of plants and atmospheric carbon dioxide. As carbon dioxide levels go up, plants photosynthesize more rapidly. This effect has been called the carbon dioxide fertilization. But as they do, carbon dioxide levels tend to fall because carbon dioxide is consumed by plants during photosynthesis. Thus the terrestrial biota tends to stabilize atmospheric carbon dioxide levels. Note that negative feedback loops occur when the loop contains an odd number of negative couplings. Negative couplings are those where an increase in one component leads to a decrease in another. Here, the link between photosynthetic rate and atmospheric carbon dioxide is a negative coupling, because an increase in photosynthetic rate leads to a decrease in atmospheric carbon dioxide, and vice versa. To help us monitor the recycling of elements through the Earth system, the concept of residence time can be useful. Residence time is defined as the average length of time a substance spends in a given reservoir that is at steady state. We can calculate the residence time by dividing the reservoir size at steady state by the inflow or the outflow rate. If reservoir size has units of mass and the inflow and outflow rate is in units of mass per time, then the quotient has units of time. We can determine the residence time of atmospheric carbon reservoir from the size of that reservoir, which is 760 gigatons of carbon, and from the rate of respiration and decomposition, i.e. the inflow rate, or the rate of photosynthesis, i.e. the outflow rate, both of which are given as 60 gigatons of carbon per year. Thus, if we assume steady state, the residence time of carbon in the atmosphere with respect to these processes is 760 divided by 60, which is equal to 12.7 years. This means that carbon in the atmosphere is replenished about once per decade. We can also think about residence time as an indicator of how long a reservoir takes to respond measurably to large imbalances in inflow or outflow. In our atmospheric carbon example, if photosynthesis were to cease, but respiration and decomposition were to continue at their current rate, the atmospheric CO2 level would double in about a decade. Thus the residence time, defined at steady state, becomes the characteristic response time when a system is not at steady state. This is the end of part 2.